Hello to everyone. My name is Alina. My field of research is homomorphic cryptography. In this work, I would like to present cryptanalysis of one recently proposed fully homomorphic cryptosystem. First, I would like to make a short introduction into the field of homomorphic cryptography. It is well known that usually cryptosystem allows to hide private data by transforming it into unreadable form. And homomorphic cryptosystem has some additional important property. They allows to compute functions and programs of encrypted data without involving of decryption key. The desirable result of computation of plain text may be extract from the result of computations of ciphertexts by the owner of secret key of cryptosystem. Here the most important thing is a fully homomorphic cryptosystem. Fully homomorphic cryptosystem allows to compute an arbitrary function of encrypted data. It's of key importance because such cryptosystem with such property may allow to make cloud services more secure. Because, for example, if there is a thin client and he wishes to compute some function over his private data, and he hasn't enough computational power to make this computation, then he may use fully homomorphic cryptosystem to encrypt his data, and he gives to the server the encrypted data, and the server do computation of encrypted data, and the server returns a result to the client into the encrypted form. So the sensitive data of the client remains hidden during the process of computation. And of course, this makes fully homomorphic cryptosystem is a very important tool to protect data in clouds. Here there is a more formal definition of fully homomorphic cryptosystems. In fact, it's usually supposed that plain texts and ciphertext form some rings with operations of addition and multiplication, respectively. And cryptosystem is fully homomorphic if the sum and product of ciphertexts correspond to sum and product of plain texts, and also addition and multiplication operation of a ciphertext must be computed efficiently. And in fact, if operation of plain texts form a Turing complete basis, then any function, any program may be computed our data in the encrypted form. For example, if plain texts are bits and operation of them are addition modulo 2 and conjunction, bitwise operation. Now there is a brief survey of existing state of affairs in the field of homomorphic cryptography. Till 2009, we are not proposed some fully homomorphic cryptosystem, and only in 2009, IBM researcher Craig Gentry proposed the first fully homomorphic cryptosystem. It was based on hard problems in lattices, and this cryptosystem was probably secure against different important types of attacks, but it's totally inefficient and it can't be used in real applications. So in subsequent works, Gentry and his colleagues improved original cryptosystem of Gentry, but still its performance is terrible and it can't be used in practice. So many researchers try to propose some alternative fully homomorphic cryptosystem, and the main direction here is to try to construct fully homomorphic cryptosystem based on the problem of big number factorization that is known, that is studied very well. It is classical in cryptography and it is known to be hard to solve. In fact, today there are several factoring-based fully homomorphic cryptosystems, and they are simple, they are efficient, they are more efficient than Gentry-style fully homomorphic cryptosystem, but there is a problem with security because for many of these factoring-based fully homomorphic cryptosystems, the authors didn't prove strictly the reduction that breaking a cryptosystem is not easier than to factorize a big number that is used in cryptosystem. And in this work, we study the resistance of one fully homomorphic cryptosystem based on factoring problem, and it was proposed in 2013 by a Russian research group from Novosibirsk. And we analyze its resistance to such important type of attack as a known plain text attack. This type of attack suggests that adversary that trying to break cryptosystem has several pairs, plain text, ciphertext, where ciphertext encrypt plain text, and the same secret key was used for encryption for all the pairs. The security against this type of attack is a standard requirement to cryptosystem, and the scenario when adversary intercepted several pairs plain text, ciphertext by eavesdropping of a channel is very realistic. Why we analyze this cryptosystem? First of all, it is simple and it's very efficient. It has very good prospects to be used in real world application. But also the authors of this cryptosystem have already used it to implement the private data storage. But security of this cryptosystem wasn't studied thoroughly. And here we fill this gap. Here let's briefly recall how this cryptosystem works. There is a big number n that is a product of two big primes p and q having equal bit lengths, and p and q are secret and n is public. Plain text is an element of a ring of integers modular pair that is finite field. In fact, we will call it ZP. And ciphertext are univariate polynomials with coefficients belonging to the ring of integers modular number n. We call it Zn. The secret key is a polynomial, univariate polynomial U, having coefficients in ZP. It is monic and reducible. And to encrypt plain text, first it is summed with some polynomial having coefficients that are uniformly random multiples of a secret number p, and then to the sum the multiple of secret key is added. And this cryptosystem is fully homomorphic because it is easy to show that the sum and the product of ciphertext correspond to the sum and the product of plain text. And also here there is a special encryption of zero plain text that allows to reduce the growth of ciphertext sizes when they are multiplied. The authors of this cryptosystem assumed that it is secure against non-plain text attack, and they supposed that the security against this attack is reliant on the problem of factoring a big number n that is known to be hard. And here we show that in fact it's not true, and it's enough to intercept only 2 or even 1 pairs to break this cryptosystem and to recover the factorization of n and to find the secret polynomial U. And the success of attack, the probability of success is close to 1. Here we highlight the main properties that allow to break this cryptosystem. We suppose that we have 2 pairs plain text ciphertexts, and there is the following property: polynomials equals to the difference between ciphertext and plain text modulo n have common factor modulo p. And this common factor, in fact, is a secret polynomial U, that is a secret key. It is easy to see if to understand. It is easily follows from the algorithm of encryption. And this property gives the strategy to analyze the cryptosystem to find the factorization and secret key. First of all, an adversary should recover P and Q, and then a secret polynomial U may be computed as a common divisor of polynomials equal to ciphertext minus plain text modulo P for given pair plain text ciphertext. To explain how P and Q may be recovered for the first step of our attack, we need the notion of polynomial resultant. Resultant for polynomials f and g with coefficient in Zn is a determinant of Sylvester matrix composed by coefficients of f and g. And there is the following important property that polynomials f and g have common root or factor modulo n pair or q if and only if the resultant is an integer equal to 0 modulo n pair or q respectively. And this is a well-known result from common algebra. And this gives us the method to recover the factorization of n for described above fully homomorphic cryptosystem. For given pairs plain text ciphertext, polynomial equals to ciphertext minus plain text modulo n have common factor modulo p. We saw it before, and therefore a resultant for such polynomials is reduced to 0 modulo p. So it's a multiple of p, and if it's not a 0 modulo n, one may compute p as the greatest common divisor of this resultant and the number n. And by the Chinese remainder theorem, here the resultant is not equal to 0 modulo n if and only if it's not equal to 0 modulo q. And the last one, according to properties of resultant, is equivalent to the fact that polynomials equals to ciphertext minus plaintext modulo q are co-prime over zq. And to estimate the probability to recover P by the computation of resultant, we need to estimate the probability that polynomials equal to ciphertext minus plaintext modulo q are co-prime. And to find this probability, we proved that according to encryption algorithm, these polynomials may be thought as uniformly random polynomials and independent, having coefficients in ZQ. And then we used the known result of Benjamin and Bennett, that two uniformly random and independently taken polynomials over ZQ are co-prime with probability 1 minus 1 divided by q. And according to this result, we obtain that we may recover P by the computing of resultant and the greatest common divisor with probability 1 minus 1 divided by q. So this is a very good probability. It is close to 1 because q is a very large number. Its bits length is about more than 1,000. After recovering P, one may compute secret key, that is polynomial U. This may be done by computing the greatest common divisor of polynomials equal to ciphertext minus plaintext modulo P. And according to encryption algorithm, this allows to recover secret polynomial with probability that is equal to 1 minus 1 divided by the number of irreducible polynomials over ZP. And finally, it is easier to prove that the total probability to recover P, Q, and secret polynomial U is equal to the product of probability to find P by the computation of resultant and the probability to find polynomial U by the computation of polynomial the greatest common divisor. And for large P and Q, this probability is overwhelming. It is close to 1. And finally, I would like to stress out that this attack is efficient. Its running time is polynomial in bit lengths of big number n, and the degree of ciphertexts of polynomials representing ciphertexts, and we implemented our attack and this cryptosystem, of course. And here you can see the experimental data. Even for large degrees of ciphertexts, the running time doesn't exceed an hour. And here there is an experimental estimation of probability to recover P, Q, and secret key U. You may see that it is close to 1, so the experiment confirms the theory. And to sum up, I would like to point out that in fact this cryptosystem is totally inefficient, is totally unsecure against non-plaintext attack because it is the authors proposed to publish an encryption of zero plaintext to reduce the sizes of ciphertexts during their multiplication. So there is An adversary always has one pair, plain text, ciphertext. So it's enough to intercept only one pair to break the cryptosystem. And finally, I would like to note that our attack is similar to. Our attack is inspired by attack proposed by Wagner on algebraically homomorphic cryptosystem proposed by Domingo Ferrer. And so the final conclusion is that the existence of factoring-based efficient and simple fully homomorphic cryptosystem that is secure against non-plain text attack today is still an open important problem. And our future plan is to investigate the security of this cryptosystem against more weak attack, that is ciphertext only attack. No, that's all.
Коллеги, вопросы?
Вопросы можно на русском.
Colleagues, do you have any questions? Questions could be asked in Russian language. You're talking about the symmetrical, fully homomorphous. Yes, symmetrical. People are trying to implement them. You have a practical implementation of asymmetrical homomorphic system, or 3 megabytes, 73 terabytes. Yes, they're applied in some very narrow private applications, so any attempts to implement them were there, but they were experimental implementations, and in fact there's no working option or draft. It's planned that in about 2 years similar gentry system would be fine-tuned for any specific narrow applications, but in general they are unclear whether it's going to become effective or not. No questions? Then thank you. Oh, there's a question. Question: have you analyzed to what extent this weakness of the proposed algorithm is a direct consequence of the improvements which they made in the original algorithm of Gentry? They did modify their algorithm of Gentry, they proposed their own. Well, Gentry Cryptosystem is absolutely different. It's based on the grid, and it's polynomial and the task of factorization. So this probably is inspired by Domingo Ferrer Cryptosystem. So they didn't analyze that for sustainability for this kind of attacks. Cryptosystem which you mentioned, yes. So they've expressed some assumptions which could be secured against attacks of the known pairs and ciphertexts. But strong reduction was not done. There was a hole in the cryptosystem. No, interesting, they have a publication. Whether they haven't made an analysis. I've realized everything is broken very easily. Thank you. Thank you, Jacob. Hello. Question could be not relevant to the subject of your report. I would like to know your opinion about what areas you see in the development of homomorphic encryption to make them more practically implementable. Well, the cryptosystems that Gentry is working on, honestly speaking, the analysis made is showing that in the nearest future, most probably nothing practically implementable will be proposed about the crypto systems and based on factorization. So far, all of them are full of holes, could be easily broken. I have a colleague who is doing the homomorphic encryption, and they're developing a alternative fully homomorphic crypto system based on the matrix polynomials. But as we know it, so we made some analysis. It's rather effective, but analysis of production still requires fine-tuning. So presumably the complication will be about complication of polynomial equality. But it's very, very complex and difficult task. But so far we haven't proved this. Well, we can say basically it's up somewhere up in the air. It's open question, open issue. We'll see what happens then. Any questions? Thank you.